Good evening. Welcome to Q&A. I'm Tony Jones, and here to answer your questions tonight, world-renowned physicist and string theorist Brian Greene, molecular biologist and co-founder of Real Science, Upali Divisekera, dark matter and energy cosmologist Tamara Davis, Australia's chief scientist Alan Finkel, and marine ecologist and presenter of Coast Australia, Emma Johnston. Please welcome our panel. Now, if you're in one of those multiple universes in Queensland, South Australia, the Northern Territory or Western Australia, you can watch Q&A live on ABC News 24 or listen live on News Radio. Well, we're giving politics a rest to explore the wonders of science. Let's go to our very first question. It's from Raina Kogan.
What does the detection of gravitational waves actually mean, and what are the repercussions of it?
Ryan, start with you.
Well, this is one of the biggest discoveries of really the last 100 years, right? Albert Einstein in 1916 predicted that there should be ripples in the fabric of space. It comes right out of his famous general theory of relativity. He didn't think we'd ever detect these waves. He wasn't even sure that they were actually real. Even Einstein didn't quite get relativity right all the time, which is sort of an amazing thing to bear in mind. But then, 100 years later, February of this year, the announcement from LIGO, Laser Interferometer Gravitational Wave Observatory, a team of 1,000 scientists around the world, that ripples in the fabric of space have finally been detected. And this is an amazing moment, not just because it confirms once again that Albert Einstein had this amazing ability to see into the deep nature of reality, but because it opens a whole new way of exploring the universe. For hundreds of years, what have we done? We've looked up into space with our eyes, with telescopes, and used waves of light to examine the cosmos, right? Now we're going to be able to examine the cosmos using waves of gravity. And that's very exciting because light can be blocked, right? Easy to block light. Pull down a window shade, you block light. Very hard to block gravity, which means gravity can penetrate into regions that light can't, which means we may be able to see things with gravity that are simply unavailable to us with waves of light. So it's really the origin of a new era of astronomy. I should say that we're here. Australia played a big role in this, right? A team of researchers at ANU, for instance, worked out a key feature of the detector, which found these gravitational waves. So you all should give yourselves a pat on the back and double down on funding for gravitational wave detection. Please.
Well, hey, Brian, we'll come back to that in a moment. Where do they come from, these gravitational waves? Because it's 1.3
Yeah, you're right. This particular example is a wonderful episode that happened 1.3 billion years ago. So it's 1.3 billion light years away, which is far. It's very far away. So it's an amazing thing. While there were, single-celled organisms floating in Earth's oceans, right? These two black holes on the other side of the universe slam into each other. They set off this tidal wave of a ripple in space. It goes toward the Earth. Roughly 50,000 years ago, when Homo sapiens are just starting to rise up and take over, the wave reaches the Milky Way galaxy, right? Then, about 100 years ago, one member of our species, Albert Einstein, sits down and starts to calculate. There may be these gravitational waves. The waves are already long since in transit. And then, September of 2015, that wave finally hits Earth's shores. And what it does is, it shakes a detector by a fraction of an atomic diameter. This is a detector in Louisiana and Washington State, 4-kilometer-long arms with lasers rushing down them. This wave goes by, it stretches one arm, squeezes the other by less than an atomic diameter, and holy cow, they're able to detect that and see that these waves are real.
Tamara,
thank you very much.
Well, I'll go to Tamara first. Are you as excited as Brian obviously is? I mean,
absolutely.
You rarely get to see this kind of excitement about a scientific discovery, but this is something special.
Yeah, this was something that was so eagerly anticipated. I think rarely have we had something that is so exciting to discover. I mean, we were really quite sure that gravitational waves existed, so the detection of it is not so exciting in that, wow, we've confirmed that. What's really exciting is that we now have a whole new way of looking at the universe. We can now feel the space ripples. It's like the analogy that I made, it was like we've been standing on the top of a cliff for our entire lives, sort of blindfolded and listening to the surf. And like all of a sudden now we've like grabbed a surfboard and we've gone out and dived into the waves, and you experience it in a completely different way. So it's like we've been given a new sense, and we can detect things like coalescing black holes that we've never been able to see before.
And maybe even the Big Bang itself.
Exactly.
I mean, this is a real exciting thing. We will never see the Big Bang because light can't penetrate through the plasma that formed just after the Big Bang. But waves of gravity can, in principle, penetrate through that plasma. We are blind to the Big Bang with light. We may see it with waves of gravity.
Alan, you've described this as the Kilimanjaro of communications. I suppose you mean by that we've scaled something unexpected.
Well, at the time I was referring to the challenge of communicating it, and you've just seen Brian and Tamara communicated very, very well. Certainly from my own point of view, this is the most exciting thing that I can recall from physics because it was so definitive. You know, black holes sort of crept up into my awareness, and dark energy and dark matter and the Higgs boson, but this was just a definitive moment in time. But the other aspect of this that I'd like to mention is the extraordinary achievement of the scientists and physicists and engineers in designing that LIGO apparatus that Brian was talking about. They started thinking about this in 1990. And back then, none of them actually believed that they would be able to do it. And if you had asked them 10 years ago, they probably would not have believed that they would get to this level of accuracy. And they kept working at it and working at it using science, mathematics, electrical engineering, everything. And they got it.
I tell you what, because it's very relevant, I think, to go to our next question right now. I'll bring in our other panellists in a moment. Ian Falconer.
The success of the Advanced LIGO experiment in detecting gravitational waves was in no small way due to the very high quality, high flatness, high reflectivity mirror coatings made by CSIRO in suburban Sydney. These are coatings that could only be made in 2 to 3 institutions around the world. That laboratory has now been gutted. And at another CSIRO lab in Sydney, there was an optical workshop that could make precision spheres, accurate to within less than a nanometre. Again, this sort of precision could only be achieved in 2 or 3 labs in the world. This workshop is now defunct. Alan Finkel, what can be done to restore these facilities, which are key infrastructure in Australia becoming an innovative nation?
It's a really important consideration, especially if, for example, we were funded to build a LIGO in Australia. The decision that I've had nothing to do with, of course, to shut down the lab that makes the coatings for the mirrors, I think goes back a couple of budget cycles. But I've been interested in that and I've made inquiries, and the CSIRO is convinced, and they've done some work to prove it to themselves and to me, that they have the basic capability, but they would have to restore that lab if we ever wanted to go that
Why did they shut
step.
it down? Alan, what's the answer when you ask them, why did you shut down something that helped to lead to this enormous scientific breakthrough? Why did they then shut it down?
So it goes back a couple of budget cycles, and it's primarily a budgetary consideration, and they're all the time juggling as to where they're going to apply their money, and they didn't see a lot of recurrent need for that capability. But as I said, they've kept some basic capabilities, some capacity, which has them convinced. And I think that it's credible that they could restore that capability. But it's difficult.
Upali, I'll bring you in here. I mean, listening to that, you've heard the sort of extraordinary story. You already know it, obviously, this wonderful breakthrough. And then we hear that we had a laboratory that contributed to it, and it's shut down.
Well, this is one of the sad things about basic research. It's always difficult to sort of see the outcome, the potential outcome of basic research that is carried out, of pure science. And this is just an example of how if you can't see what an outcome is, you make a snap decision based on a budget. The problem is once you close these sorts of facilities down, you can bring it back, but you've lost that capacity. You've lost something that was already built up and ready to go. And so that's one of the problems with shutting down these sorts of programs. So that's also just another sign that basic research is really, really important.
I'll bring Emma in here. I mean, you spend most of your time underwater, or a lot of your time underwater, I should say. But I mean, I imagine you look up at the stars, and I imagine when you heard about this breakthrough, you would have been pretty astonished as well as a scientist. So can you reflect on how you feel not only about that, but about the question that just came in about the shutting down of those laboratories?
Well, I think the ripples of excitement went through the entire science community and probably the whole world when this development was announced. The thing that I still get excited listening to everyone here on the panel talk about it, because it reminds me of one of the greatest glories of science, is that we look at the world in so many different ways and on so many different scales, and we don't ignore each other. So whilst this kind of finding might not immediately help me work out, how the elephant seal is moving around the Southern Ocean, I don't disregard it, and I also try and build it in, layer upon layer, theory upon theory, in the way I understand the world. And that's how we work. And when governments are clever, they fund research at all of those different scales and all of those different approaches. And when scientists are clever, we listen and accept the findings from research from all of those different approaches, including social sciences.
Tamara, I'll bring you back in here to reflect on the second part of that. That is the closing of the labs.
Yes, it's a shame when you've got to keep the continuity somehow, because once you've lost that knowledge, it's really hard to get it back. So if you close something down, I think there's more than just this particular lab being shut down in CSIRO at the moment. So when you shut something down, it's really hard to bring it back. It's something that has to get sort of continuous funding.
Okay, it's not the only area that's been cut. Our next question is from Mohammed bin Zunaidi.
Hi, Tony. Thanks for the opportunity. I just want to ask, what's the consequences of this climate change cuts? And also, is part of the reason for that cuts because the general population does not understand the significance and the importance of climate change research and its effect on the world?
Emma, I'll bring you back in here because the climate change cuts, we're referring now to 350 staff from CSIRO who've also lost their jobs, climate change researchers.
Yes, it's very difficult. We've just had some astounding news today, in fact, announced that we've had one of the warmest February on record, and it's 1.5 degrees above the average global temperature for the pre-industrial era. So this is this is a surprising thing even to scientists. And what I think it emphasises is the need for measurements and modelling beyond what we already have. So we know, and the science about how climate change takes place, the way that carbon dioxide and other greenhouse gases trap heat in the atmosphere, that science has been settled since before most of us went to primary school. But what's still a really active question is how climate change is going to play out on fine scales and what all of the positive and negative feedback loops are. And that's where our measuring and our modelling and our global attempts to integrate measuring and modelling are so crucial. They're crucial to farming, they're crucial to fishing, they're crucial to industry. They're actually of massive national interest. And, if we want to be able to make predictions that are important to the national interest, we need sustained funding of very fine-scale measurements and modelling.
I'll just quickly stay with you just for a moment because you've spent a good deal of time on the Great Barrier Reef, and the big fear there, and it appears already to be being realised, is of coral bleaching on a large scale. Do these new temperature figures create even bigger fears for the Great Barrier Reef?
That's right. So I was on the phone to the Great Barrier Reef Marine Park Authority this morning, and we are in the middle of a bleaching event, a global bleaching event. And it's been confirmed for the Great Barrier Reef is actually bleaching on a greater scale. We were observing patchy bleaching previously, but today they've upgraded that to severe bleaching in some sections, particularly the northern section, which is our most pristine part of the Great Barrier Reef. So it's the part that you would expect would have the strongest resilience to this kind of effort. But the waters have been warm enough for long enough that the corals are expelling their zooxanthellae. These are little microalgae that live in the coral that provide up to 97% of the food for the corals. So if they bleach, they lose those. If they bleach for long enough, if the waters stay hot for long enough, they die. and they don't recover from that. So we don't know how bad this bleaching event will be. It'll take quite a few weeks for us to be able to monitor that. The Great Barrier Reef Marine Park Authority, AIMS, all of the researchers up there are out looking, they're trying to see what's going on, they're measuring temperatures, they're looking for bleaching, and they're trying to establish to what extent we'll have a major bleaching event.
Alan, I'll bring you in now, and can I get you first just to refer, we'll go to the business of the scientists who've lost their jobs in a moment, the researchers anyway. But I'll bring you in just on the temperature question first, because it's today's news. A 1.35 degree increase in the past month, according to at least one climate scientist I've seen quoted. It's unprecedented. He's talking about an emergency, a climate emergency. Is it too early to say that?
Look, it's probably too early to say that, but that rise is consistent with the trend. So even though it's 1 month and it's almost aberrantly high, you wouldn't want to dismiss it. There's genuine reason for concern. And it's also consistent with another figure that came out yesterday, which was the measurement from Hawaii of the level of carbon dioxide in the atmosphere, not the emissions, but the actual level. And they've now determined that it's gone up in 2015 by 3.05 parts per million, just over 3 parts per million. And that turns out to be the largest annual increase since recording began more than 50 years ago. And what that says is that for all the effort that we're putting into trying to avoid increases of emission, we're losing. So what we're doing with solar and with wind and changing practices, behavioural practices and things like that, we're not winning the battle. And as Emma was just saying, carbon dioxide, it's just basic physics. It's a greenhouse gas. It traps infrared, and if carbon dioxide levels go up, there will be increased heating. Exactly what the ramification of that is in terms of local and regional climate change is very difficult to work out, and that's why they do all the modelling. But there will be consequences. And so the temperature rise is not necessarily directly linked at that magnitude with the carbon dioxide increase, but they're all part of the same bundle.
So if we're losing the battle, as you said, why would we kill off 350 of the troops in that battle? The climate change researchers who've just lost their jobs.
Well, look, first of all, just a few things. And again, I'm not part of the CSIRO, but the numbers are 350 total, not just in climate research, but across a number of different areas of the CSIRO. And it's part of their reprioritisation, and their intention is to rehire 350 people over the next 2 years. So ultimately they'll have constant numbers, but they are looking at letting go a large number of climate scientists. Their stated
Do you know
reason,
exactly how many, if it's not 350?
well,
It's been widely reported.
I don't know exactly, but I think
350.
that, of 100 they might be reducing down to 30 or 40. So substantial reductions in the climate research area.
Does that make sense to you?
Well,
as a chief scientist talking about this battle that's being lost, does that make sense?
Well, there's multiple aspects to the battle. And one of them is what they're trying to do, which is look at how we adapt and mitigate. And so what they're saying is they're working within a fixed budget envelope, and they want to put resources into agricultural improvements to deal with the heat and the other changes. The critical thing, though, is, you already mentioned, and Emma did too, the measurement capability. And they have committed to keep the measurements going at Cape Grim and the marine measurements going. And that's important because if we have a gap in our recording of data, we can never, ever come back and fill that gap.
Okay, I'm just going to go to Upli here again. Listening to this is two groups of scientists now, one in an experimental area, another one in the battle against climate change, losing their jobs. Can you understand why this is happening?
I understand that every organisation has to undergo some form of restructuring and review over periods of time. But it's a shame to sort of lose this, again, going back to that issue of losing capacity. You've invested in this. You've built up these laboratories and you've built up this expertise, you've educated these people, and then you just let it go. And it's understandable that there are always budgetary constraints, but you're letting go of this excellent, irreplaceable expertise. And the other thing is that this expertise exists to serve the nation. CSIRO and the climate change scientists in that organisation exist to help us future-proof Australia for the inevitable climate change that's coming for us. Well, that's going to affect the land mass. So the fact that we're losing, we're going to lose our inbuilt capacity And inbuilt, we have measuring systems. All of this is available to us right now, and we're just letting it go. So it's a shame.
Yeah, Brian, I'll just get a very brief response from you on this. You've listened to it, you raised it, you said, please don't sack these scientists.
Yeah, well, I mean, this particular issue I only recently became aware of, having just visited your country, a week ago. I haven't been following it in great detail, but it seems to be part of a larger trend that's happening in America too, which is a shift from funding the actual basic underlying fundamental science and shifting focus to applied ideas that might have some economic impact, that might have some partnership with industry, where everybody can have some economic benefit from the research. And goodness gracious, I understand that everybody wants to make money on their investment ultimately, but the engine of innovation, the engine of progress is the basic research. So let me just tell you, if in the 1920s people looked at those who were developing quantum mechanics, which seemed kind of esoteric, right, pretty far from everyday life, and say, you know what, that's not going to have any impact, so let's cut that. You know what the impact on that would have been? Any person that has a cell phone, which is everybody, personal computers, MRI machines, anything with an integrated circuit, it all comes from the basic physics that was done in the 20s on quantum mechanics. Quantum mechanics is now responsible for something like 35% of the gross national product in the United States, and probably something similar here. Basic science is critical to having the economic impact in the future. If you don't invest in that, you're sacrificing our children, because you'll be running on fumes pretty quickly.
Okay, we're going to... Thank you. All right, you are watching a special science edition of Q&A. You must have noticed by now. Let's go back to theoretical physics. Our next question comes from Claudine Bautista.
Hi. If we do have a multiverse, if it exists, how will it affect the way we live?
Brian, I guess you're asking me.
Well, you're the multiverse man.
Yeah, in this universe,
panel,
apparently I am. How will it affect the way we live? Ultimately, that, of course, is a very personal choice on how one embraces scientific insight, integrates it into one's life and worldview, and how that affects how you go about your business. But what I will say, it would be one of the most dramatic upheavals ever to our picture of how reality is constructed. I mean, we've all thought that what we see out there is more or less reality, right? The stars, the galaxies, we've learned about dark matter and dark energy, all sorts of wondrous stuff that's out there. But pretty much what we can see out there in the universe we thought was the be-all and end-all of everything. And then along come mathematical theories that do make some contact with observation, like inflationary cosmology, or areas that I focus on, string theory. And the math suggests that what we have long thought to be the universe might be one small part of a much grander whole. And the grander whole might have other realms that would rightly be called universes of their own. It is a very strange picture. In fact, one of the early people who came up with this idea found it so distressing, because the math actually shows, and this is kind of weird, but this comes right out of the math, that if there are these other universes, and if there are perhaps infinitely many of them, which the math seems to suggest if these ideas are correct, then there are going to be copies of you out there. There are going to be copies of me out there. We're going to be having this conversation over and over again in universe upon universe upon universe. So it kind of strikes at the notion of personal identity. Who are you? Right? Are you this one in this universe? Is that one you too? Are you separate individuals? It's a mind-boggling thought that has deep philosophical ramifications. But again, we don't know if this idea is correct. We only will believe it if there's observational or experimental support, and there are possible ways that that actually might happen.
Tamara, are you convinced about the mathematics of string theory? Because it hasn't been experimentally proven, but it's a wonderful theory.
Oh, it's glorious. It's so elegant in many ways, and yet we haven't actually confirmed it observationally. So that's the gold standard. We want to see things observationally. So string theory is one of the possibilities for how we can combine quantum physics with gravity, which is one of the really important things that we need to do. We know that those two theories don't play well together. We know that we haven't found the final theory. So
the unified theory.
The unified theory, and there's tantalizing hints from observations for things that we need to explain. I mean, and the acceleration of the expansion of the universe is one of them. And, maybe we need this to be able to answer that.
What evidence would you require as a scientist to accept that string theory was real?
I think typically with most predictions, or with most theories, what you really want is the theory to make a prediction that you can go out and then test. You know, the theory you can build up a theory that explains everything that we know, but then when that theory goes and predicts something that you can then test and go, whoa, we were right, that is when you have something that's really solid. So the gravitational waves is a great example where relativity is, it's been tested in so many ways now, but this was just one more way in which the theory said, hey, space should curve and ripple. And we go out and do these things and we measure to fractions of a nucleus the distance of these arms of an interferometer, and voila, it works exactly the way we predicted. I think it's astonishing the way that we can use mathematics to build up this theory and then predict that stuff should exist. I mean, it happened before with the Higgs boson as well, and multiple times in history.
It was exactly what we're talking about with Einstein, and of course it took scientists 40 years to come up with gravitational waves. Maybe it'll take longer, Brian, but we've got another question to get string theory proven, but we've got another question on this subject. We'll go to that. It's from Daniel Clark.
Hi, Brian. It has been said that the multiverse theory, while it explains the Goldilocks enigma, so why our universe is right for life, it's just pushing the question of existence up another level. Instead of us asking what led to the universe, we're now asking what led to the universe generating mechanism and what led to the unified laws of string theory. So my question is, while it's all well and good to have this unified model, what's the point in pursuing it if we're just getting more unanswered questions?
Brian, what's the point?
You know, I never quite thought of it. You're right. I'm going to retire. No, here's one way of thinking about it. Science is not really about finding the final answers per se. I mean, sometimes we do have a body of research and we find an answer and that kind of ends that arena, and then we go on and study other things. But when we're talking about the fundamental laws of nature, when we're talking about where the universe came from, when we're talking about these huge, big ideas, almost anything that I say to you, you can say to me, well, why that, Professor Green? Or if you know me, you may say, why that, Brian? Right? You would say that, right? So at some point, what we really view progress to be is just having a deeper, more powerful, more all-encompassing, more elegant, more complete description of what we observe, even if, as you're saying, it might not be the case that there isn't yet another question to ask. That's really what the nature of progress in this kind of science is about. Does that address the question? You know, I should say my mother asks exactly the same question, but it feels so familiar to me. But yeah, go ahead.
Yeah, it also just seems to be like this theory is just creating things which are really, really hard to prove.
Good. Now you're going in a slightly different direction, which is a nice direction to go, because it is not the case that string theorists sit in their office late at night, have nothing else to do, and start to come up with these wild, crazy ideas. Maybe there are other universes, or maybe there are little membranes floating around, or, you know. What happens is we sit there with the mathematics, and we use the standard techniques to develop our equations. And then the equations grab us by the lapel and slap us and say, look at what I'm telling you. There may be other universes. And we go, whoa, holy. I promised I wouldn't say bad words to the producer, so I won't. But you see where I'm getting. It's not the case that we inject crazy, wild ideas for the sake of doing it. We sit there quietly, sober, follow the equations, and see where they take us. And that's where these ideas come from.
Brian, I've got to throw in, you probably want to ask the same question, but I'm going to ask it anyway. The Large Hadron Collider was potentially a way of proving that other dimensions exist. These particles would collide and throw off other dimensions, or into other dimensions. This did not happen.
Yes.
Is it possible that there is no machine capable of proving string theory?
That's a very good question, because if the answer to that were yes, I assure you I would not work on string theory. I assure you that no string theorist would work on the theory at all, because if the ideas were somehow fundamentally unprovable, fundamentally unable to make any contact with observable physics, then it's hard to see how we would be doing science. But it's very different from saying it's very hard for us to test these ideas, that it's a long shot that the Large Hadron Collider has enough power to create the collisions that would send particles into other dimensions. It might happen, but it's a long shot. So look, it could be when the machine is on, right, in the next couple of years, could it be the case that we will slam protons together near the speed of light and some debris will leave our dimensions and enter another, as the math says might happen? It may happen. I am not holding my breath. Between us, I think it's unlikely. I think it's very unlikely this is going to happen. But nevertheless, it just shows how difficult it is for string theory to be tested. Let me just add one footnote, if you don't mind.
But I'd like
you got to move on, but I just got to give you one little footnote here, which is this.
Sure.
This is not.
I've read your papers; they're full of footnotes.
This is not a string theory issue per se. As Tamara was saying, string theory puts gravity and quantum mechanics together. Any theory that puts gravity and quantum mechanics together will really show its true form, its true color in extreme realms, very, very tiny scales, huge energies. All such approaches are going to be very, very difficult to test.
Tamara, do you think that's right? I mean, are we in the period that scientists were in 40 years ago when they decided to test for gravitational waves?
Well, this is why I love astrophysics. Why I study space, because the Large Hadron Collider might be a 27-kilometre around ring at which you accelerate things to close to the speed of light, bash them together, and from the shrapnel try and figure out what matter's made of. But it is still only a 27-kilometre around ring on like a puny little planet around
a $20, $30 billion.
Yeah.
What's that?
Yeah, it's nothing, right, compared to military budgets. But. We're orbiting...
If only you could make a bomb out of it, you get a lot more money.
Yes. But we're orbiting a much larger star, which literally does have a nuclear furnace going off in the centre of it, which is just one of hundreds of billions of stars in our galaxy, which has a supermassive black hole in the centre of it. We have cosmic rays hitting our atmosphere all the time at energies that are greater than we can create in the Large Hadron Collider, which incidentally is one of the reasons why we were not that worried that the Large Hadron Collider would make killer black holes that would suck us all in. And there's hundreds of billions of galaxies in the observable universe, all with these supermassive black holes. So up there, we have the energies and timescales and length scales at which we can test fundamental physics in ways that we just can't even really, in principle, do here on Earth.
Well, we've got the chief scientist here, and I'm sure you'd want to go to government and suggest they build an even bigger Hadron Collider. Just get rid of a few of those submarines and you could build one in, I don't know, Alice Springs.
Well, we've got the perfect location in Western Australia, not far from where we're building the low-frequency SKA, the Square Kilometre Array. But I would say that if you'd asked me 2 months ago whether I had any confidence at all that Brian and other string theorists' work would ever lead to something detectable, I'd say no way. But now with the LIGO proving gravitational waves, even though Einstein 100 years ago said he didn't think it would ever be testable, and the development team 10 years ago saying we probably can't get there, we've shown what we're capable of doing if we apply ourselves. It's stunning.
OK, we'll see you in another universe. We'll get back to a different question, though. Remember, if you hear any doubtful claims on Q&A, none of those are doubtful. They're theories. It's probably just unproven theoretical physics. So if you think it's wrong, send a tweet using the hashtag #FactCheckAndQuanda. And our next question comes from Jacinta Rees. Hello, Jacinta.
So how did baby turtles find their original beach where they were born when they're grown up?
Emma, that's for you.
Finally.
Water waves.
That is a beautiful question because baby turtles are gorgeous. They look like they're battery powered actually when they hatch out, and they're like on automatic. And when they first hatch out, they're actually using light to find the ocean. So they're looking for the reflectance of the moon on the ocean. So you know that bit. And then when they hit the waves, they actually use the angle of the waves to direct themselves out to sea. You know that bit. So how do they find themselves all the way back home, maybe 13, 15 years later to breed? Because they do take a long time to become reproductively mature. And that's been a really big question. And we now know that they use the magnetic field, which is another cool way of seeing the world, right? And lots of animals do use the magnetic field to navigate. So there's an amazing magnetic field because we've got a liquid core here in the world, and they can actually detect it. Now, just exactly how different animals do this is the really big question. We're coming up with all sorts of fancy names for things that we don't know, a bit like string theory. So, well, magnetospheres, you know, for detecting magnetic fields. But what we do know is that when we play with magnetic fields, the little baby turtles get confused, right? So that's the kind of indirect proof that that's what they're using. And also, just recently, because it's sad, but magnetic south is wandering around, you know, so it makes it really confusing. You go down to Antarctica and you think you're going in one direction with your compass and you're not, because magnetic south has wandered off into the ocean. And so this confuses the baby turtles as well. So they can actually show now that turtles will end up in a slightly different spot because of the movement of the magnetic field, depending on how long it takes for them to get home.
Now, can I do something a bit unusual? Jacinta, would you mind if I ask you a question? Because we met you at the beginning of the show, and I heard you do something a bit remarkable, which is to recite pi to, well, I know you can recite pi to quite a lot of decimals. How many?
I can do it to 88 now.
88 decimals. Can you just give us like a dozen?
Okay. 3.141592653589799323384623383279502881971971.
That's really more than You went on longer than you were supposed to, so I'm going to take that as a comment and move on to the next question. The next question is, in fact, from Lena Wang.
Okay, so in Korea, we've just seen Google's AlphaGo AI defeat the world Go champion Lee Sedol. So historically, automation of jobs, such as the invention of the printing press, has inevitably overtaken and supplanted no longer competitive human labor. So Alan Finkel, as the chief scientist, what's your position on the inevitable job crisis that will arise from when one of Google's AIs, the self-driving car, arrives in Australia? And also, do you think there are any industries safe from automation?
Taking the last point first, I don't think there are any industries safe from automation, but I'm not convinced that the job losses are inevitable, because what's happening is with the automation, companies get a head start, they're competitive, they earn wealth, and they reinvest the wealth. People and companies reinvest the wealth, and I don't know how it happens, but it's a result of human ingenuity, innovation, invention. New jobs get created. And so when the economists say what's happening in the next 20 years, they're all predicting in every advanced country that at least 45 to 50% of the jobs that we know of today will disappear in the next 20 years. But there will be replacement jobs.
But will anyone bother to play Go anymore?
Well, I think yesterday the Korean champion won the 4th of the 5-round series.
Yes,
so
yes.
It was a victory for humanity.
Lost three, won one. I'm going to quickly go to our next question, actually, which is also on the subject of AI. It's from, and we'll bring everyone else in. It's from Tom Henderson.
Stephen Hawking has said that artificial intelligence could possibly lead to the end of the human race. Basically, as a young person living in Australia, what should we be concerned about this issue, and what can we do to combat it, if so?
Upali, I'll start with you on this. Should we be worried that artificial intelligence will become self-aware and take over?
Well, I think until the event was lost by a human the other day, I was actually not concerned that AI was going to take over anytime soon, because the AI that we have is really not terrifically advanced, and it's still in development. But I think in terms of the future, like, we have the power and we have the ability to construct the AI that we want to see. And we have to think about how we want our society to look in the future and what sort of ethical framework that we want to introduce to develop the artificial intelligence.
Well, Isaac Asimov thought of this a very long time ago. He had the laws of robotics.
Indeed.
Yeah.
Indeed. So
is that what you're talking about?
I
mean, an ethical framework for artificial intelligence should perhaps include the provision that no robot should harm a human. That's number one rule.
I think that's a really important, probably the most important rule. But at the same time, it's when you're considering what sort of jobs that they're going to take over, you have to take that into account, what kind of economy, what kind of society that you want to have in the future. And indeed, it's the ethics of how that AI is constructed is also critical. And that's kind of up to social scientists, I think, as well, to do that. So we can also talk all we like about the automation of jobs, but there are a lot of jobs, I think, that won't be automated, that can't be automated, and most of those are menial labour, menial jobs as well. So we don't want to end up in a society where there's still an underclass of people who are still carrying out these old-fashioned menial jobs while we have automation for other things. So all of these things play into how we develop artificial intelligence.
Brian, why do you think Stephen Hawking is, and many other tech experts, entrepreneurs and so on, are so worried about artificial intelligence that they see it now as an existential threat?
You'd have to ask their therapist. I mean, I don't really know. I don't really know. But I guess my view, you know, at least I'll throw out the following question. Is the form of life that we're familiar with, is that necessarily the one that we want to stick around for time immemorial? How about the possibility that we are just in a new stage of evolution and we will migrate from this form to another form? And that might be the natural order in which evolution takes place in a technological era. I'm just joking. No, but seriously, right?
But I'll take you back to the point that Ripley just made, which is there may be a need to instill in machines a series of ethics, as Asimov predicted. And of course, the one area that's already being broken because of military artificial intelligence.
Yes, for sure.
Is that killing machines are being made which are autonomous.
Yes.
That's part of what they're worried about Hawking and others.
Absolutely so. I mean, we just had, we were just at the World Science Festival in Brisbane. We had a whole program called The Moral Math of Robots. It was all about these issues. So yes, it's important to think these questions through. It's important to envision that we do have control over the AI that we create. But I guess I'm just a little bit wary of the status quo in the sense that necessarily we have to preserve the biological form of life that we're used to.
Tamara, what do you think?
I think that, there's a huge issue with the ethics, and it's very interesting. Like, the one thing I'm really curious about is you've got driverless cars and someone has to program how they react when a kid runs in front of the car. And, there may be 4 people on the sidewalk that the car can choose to swerve and hit the 4 people and avoid the kid, or not. So what's the car's going to have to make that decision at some point.
What about when there's 2 of them sitting at the lights trying to work out whether they're going to race off in front of the other artificial car?
Who's going to drag race? But I would like to think that that ethicists and as we can actually program something into there that would actually be potentially better than what a human might do in the.
But the Pentagon's already way past you here. They're already, as I said, they're already building machines which are autonomous killers.
I know. It's quite frightening.
But if we could be immortal by uploading ourselves, again, this is all sci-fi stuff at some level, of course, but as long as we're opening the question, if you could be immortal, but in the form of a silicon-based being, would you make that move? I would.
So, I can see you've got to get something out on that.
Well, no, I was actually.
Would you make the move? I mean, you're very grounded.
I don't know. I like playing sport, and I don't know if how that would work in
Why not?
At body. But the thing that I find really curious is, we're now able to make bionic ears. We've got bionic eyes potentially. We've got bionic limbs. You might be able to create eyes that can see in X-rays and infrared and stuff. So you're going to want to have those instead of your normal eyes because those are, better. Don't have to wear glasses, but you can imagine you just replace pieces of you, and then eventually you upload your brain into a silicon version, and all of a sudden there's no biology left. And at what point along that transition do you go from being human to not human?
I think it's pretty clear, really. The point where you upload your brain.
Upload your brain?
I suspect. Alan, what do you think? You're prepared to upload your brain at some point?
I don't want to be
You've got some other form of superannuation coming in?
I don't want to be defeatist. I actually hope that the biological form of human beings is maintained for as long, forever. We have dealt with all sorts of difficult technologies, whether they're military or civilian, over the years, whether they're displacing jobs or just the danger of vehicles on the road, and we do deal with things. Just very quickly on the upload, technology is marching ahead at an extraordinary speed, as we all know. But our ability to understand the human brain is, in a sense, plodding along. We're making advances all the time, but just like all my life, hydrogen fusion is 20 years into the future. All my life as a neuroscientist, I feel that we only understand about 1% of what we need to know to fully understand the human brain. So I do not think that in 100 years we'll have the ability to do the upload.
How about 100,000? How about 100,000?
Eventually,
right?
even though the computer will have that capacity to accept the upload.
Yeah.
It might be difficult.
Right. Let's move on. We've got a few questions to get through. A lot of people have sent terrific questions in. This one's from Christina Kirsch.
This is a question for Emma, actually. And with the rising sea level and the increasing severe weather events, we see the erosion line moving inland. So what are the implications of the current Australian policies that allow the construction of seawalls to protect private property? Will we sacrifice the beach, the public asset, in order to protect private property? So who owns the beach when the sea level is rising?
Emma.
It's a really good question. And obviously coastlines are quite dynamic. So sometimes they're eroding and sometimes they're growing, depending on what part of the coastline you're on. When sea levels are rising, yes, you generally have more erosion, but it also depends on the storm conditions. What I would say is that we are constructing and have constructed and built into the marine environments much more than we think about. So, for example, 50% of the Sydney Harbour foreshore is already completely constructed, modified. It's not natural anymore. And you can say the same for parts of Europe. Just in the next 10 years, an area the size of Melbourne will be built upon in the North Sea just by the UK building wind farms into the North Sea. So we are what we call marine urbanising or marine building. And I know we're talking about sci-fi, and we've been thinking about underwater cities and sci-fi for a long time, but it's really happening. You know, we're really building into the ocean. And when we do that, we completely change the construction. We change the dynamics, we change the species, we increase the number of invasive species, and that's going to happen to a greater extent as we try to protect expensive infrastructure. Now, we can have programs of what we call managed retreat, and that's going to have to take place, and sometimes that's going to be the cheapest way to go, and that's where essentially people leave their homes and leave their buildings because the sea level is rising too quickly, and those areas become natural again, in a sense.
Is there a timescale for that? Are we talking generations, or are we talking the next decade or two?
We're talking in both. So approximately 80 centimetre rise by 2100. So we're talking fast sea level rise, and we don't know whether or not that might also be an underestimate. So very rapid change. And also, that's just the basic sea level rise. We've also got so much more energy in the system that our storms are more intense, they're potentially more frequent, depending, again, where you are. We've just seen the strongest storm ever recorded in the Southern Hemisphere, Cyclone Winston, hit Fiji. And so, you know, we don't quite understand, and again it comes back to better predictions and better models. The ocean climate interactions are incredibly complicated, and we're only starting to get our head around it. Again, if you want to talk about seeing things, we can't see under ice very well. So we go to the extent as marine scientists of sticking like instruments on the heads of elephant seals and sending them under the ice to record things for us. And that's how we're getting a lot of information back about crucial aspects of the Southern Ocean, which is driving a lot of our climate. So we're still just beginning to understand these feedback systems. What we do know is that we're building more and more into the ocean, and we can build better. So managed retreat's a great idea. Where that's not possible and we know we're going to build, for example, who wants to lose the Opera House? No one, right? So they're going to build to defend structures like that. When we do that, we can eco-engineer them so that they're more like natural structures rather than just build a straight wall. So we need to think about multifunctional structures. On land, we build green roofs. In the ocean, we just build a wall. We can do much, much better than that, and we know how to.
Okay, I'm going to move on because we do have, as I said, plenty of very good questions. The next one's from Emma Gray.
So I'm currently doing my PhD, and when I discuss my happiness, essentially, with my peers, I find more of my female peers are unhappy in their career choice than my male peers. Maybe that's just my observation, but it is what I observe. So do you think the reason for the kind of dominance of males post-PhD stage is just because a lot of females leave to have babies, which is the kind of normal answer, or is it because as females we kind of object intrinsically or find something intrinsically abhorrent in the current way that science is reviewed or the kind of way we're measured as scientists?
Upali, I'll start with you on that. What do you think?
I think there's definitely a difference in the way that women in science are responded to and are assessed and regarded by their peers, and particularly by their male peers. And there are studies that show that this begins at the undergraduate level. And so when you're advancing through scientific careers, going on to honours and PhDs and so on, it starts out being 50-50 at undergraduate, and then, you know, tails off to faculty levels of about 20%, 17 to 25% or something like that. I think part of it is due to the attrition. Like, if at some point, you know, many women will go and have children, and it's very difficult to get back into the workforce after that. It's particularly difficult in the sciences because you're judged by your publication and your research output, and once you take time off to do it, it's very difficult to get back into it, and to then it's again getting that capacity back into play. But there are also, I think, a lot of more subtle exclusions that go on. There's definitely a much harsher assessment. There's more sort of subtle social cues that happen where there's an unintentional inherent bias within people that's part of the social construct. I've been in labs where, you know, the male postdocs and students will wander off and, you know, have a chat about the science, and then all the other female postdocs and PhD students are sort of going, well, where did everybody go, and why aren't we part of this conversation? So there are a lot of structural and social attitudes that we have to overcome.
Brian, let me bring you in here as a male scientist. I mean, is there a kind of inbuilt sexism in science, in areas of science?
If there is, I don't think it's specific to science per se. I think it's a more cultural issue that invades a lot of arenas. Certainly in America, at least, I've seen a good deal of progress. You know, we have gotten closer to parity, 50-50, at various stages in the academic progression of students.
Is that through affirmative action policies?
No, I think it's really that the culture is starting to shift a little bit.
Is it a generational shift, do you think?
Well, it certainly is generational, but if that's causative or just a correlation, I don't know. But certainly, you know, my own graduate students right now, I've got one male, one female, and I've had a number of female graduate students. Some of my best have been female graduate students. And look, we try, at least, I talk to myself, I try as hard as I can to not have these kinds of issues that you're referring to, the subtle cues that somehow are singling out the women over men, but it may be that I'm not aware of it. I could be a callous, you know, cow of a man. I don't know it, you know. I try not to, you know, and I think that's true of many of my male colleagues.
Tamara, what do you think?
Well, I've never felt anything but fantastic support from all my male colleagues and male and female colleagues, but I think the thing that we're fighting against most is the stereotypes. I was working at a university in Copenhagen, and we had this celebration for the centre after it had been around for 5 years, and one of the sort of elderly male professors came up to me and said, do you know what's fantastic? It's like, you've really shown that you actually can employ women and not decrease the quality. I was like, oh, thank you. I didn't realise that was under question.
Well, this is why gender diversity and diversity generally is really important in science, because you can't be what you can't see. You need to have these examples there in high faculty positions to show you that you can reach that goal, and this is what it can look like.
But that's part of it. So part of it's, you know, historical legacy, unfortunately. I mean, it started as a male, let me talk physics, started as a male-dominated subject, which means there weren't the role models and there wasn't sort of the culture, and as that begins to shift, I think it's all going in the better direction. But it started in a pretty bad place.
With just Marie Curie.
I'm going to bring Emma in. Go on.
Well, I love the optimism that you're showing, but it's not backed by the evidence. So, unfortunately, the trickle-down effect, if things are trickling down, it's treacle, man, it's going slow. So, you know, we know that there are major structural things that need to change about the way we've created these science careers to ensure that we don't, you know, enforce an undergraduate degree of 4 years, a PhD of 4 or 5 years, and then 6 years of postdoctoral work where people are expected to move every 2 years in order to get the credentials to get a secure senior position, that's a recipe for knocking out any woman who wants to have children and who's made it through that level. And that's a key point at which we need to restructure and envisage ways of enabling women to go out, have their children, have a secure job, have maternity leave, and also enable fathers to take paternity leave so that that is a more shared option and everyone's happier, of course. But we also know that culturally these problems exist. And until you change the dominant person type, then cultural stereotypes will be there and stereotype threat will exist. So someone like me will be less confident about my capacity to do science because I am one of only 17% of professors in Australia who are women. And that's something that hasn't changed since the 1960s, and indeed some people think we're going backwards. The good news is the Australian Academy of Science, the Australian Technological Societies, all of the universities, they're signing on to a whole suite of policies and changes that are really constructive, that are addressing both the structural and the cultural problems that we face to increase not only gender equity but also other forms of diversity within science.
So, Alan, let me bring you in here. And we saw Jacinta before, 10 years old. Is it going to take until Jacinta is ready to enter the science world, quite possibly, that things might really change?
Well, I think we are looking at generational change. It takes time. If you go back 50 years ago, the undergraduate population was 20% female, 80% male. Now it's swung, it's 60% female, 40% male. And that will have an impact over the next 10, 20, 30 and 40 years, a positive impact in terms of female participation. I know from my own personal experience at Monash University about 10 years ago, the number of females at senior levels was just over 20%, and now it's over 30%. And that, we want to be further along, but that's a good trajectory. And I think you've got to be careful about not looking at the snapshot of where we are today and give more credit to the improvements that are being made. And yes, the Athena Swan program that's being
You
put forward,
shaking your head there.
will make a big difference.
You don't go for the incrementalist idea.
Monash is doing extremely well, so I'm very pleased with that progress. But not all universities are going forward. Some of them are going backwards, and I think we need to recognise that because things aren't moving fast enough. And I agree, it's not just in the university sector and it's not just in science, it's in business as well. There are more, we've got lots and lots of male CEOs. I think there's more named Mark and Peter than there are, like 4 times as many called Mark and Peter than there are women as CEOs. And that was fact-checked by the ABC a couple of years ago. But yeah, it says something about how we name our children, but, that's beside the point. The thing is we need to make faster change and also have role models. I love science. The reason I'm in it is because it's so exciting. It's such a great career and it never gets boring. Women should be able to access those jobs that are so exciting. And I think to answer the original question, where you indicated that women aren't feeling so happy, I think the thing to hold on to is how much you enjoy the actual research. And that structured inquiry and finding data and working things out, because that's what will get you through some of the tougher times while we change the structure and the culture.
Okay, thank you. Thank you. Okay, we're coming to the end of what has been a very fascinating discussion on science and gender equity, among other things. Our next and last question comes from Arthur Teal.
Brian Greene. In your work, The Fabric of the Cosmos, you emphasise that a passion to understand the universe at a more fundamental level is one of the most important motivations a scientist can have. In Australia, the government's recent innovation drive has been reminding us that science education is the pathway to future jobs. Do you feel that an excessive emphasis on the economic value of science research belittles its inherent value and fails in engaging the public?
Yes. Maybe I'll just follow on with that for just a moment. I think as we discussed a little bit earlier on, I think there is a place for thinking about jobs and economic development and impact of that sort coming from basic science. But the bottom line is we don't do basic research for that reason. We do it for the reasons that we heard a moment ago. We are on a journey that began with, say, the ancient Greeks to figure out the basic structure of matter, the fundamental laws of the universe, where the universe came from, the nature of space and time, whether there are other universes, whether there are extra dimensions. These ideas are so fantastically exciting and interesting, and to be able to be part of that multi-thousand-year-long quest to understand some of the answers, that's where the excitement comes from. And if there's an economic benefit to it, fantastic. But the true motivation comes from a deep human spirit of discovery.
Upali, bring you in.
I'd say I would agree so much with that. But I think the main thing is like these are very human inquiries. These are very human needs to know our place in the universe, to understand how it works. It's part of our nature. And the pursuit of knowledge is important in itself for that reason, because it's just understanding how everything works and where we belong. And yeah, if we make some great discoveries and a bit of money on the way, that's great. But that's really not it. It's the beauty of the universe and the beauty of the things that we study that keeps us going in it.
Tamara, I'll bring you in. Astrophysicists in Australia discovered Wi-Fi. Someone made tens of billions of dollars, not us.
We got some of that.
Yes,
With the patent was quite
180
lucrative.
million out of...
I think it was even more than that apparently, but
Okay.
But yeah, there's when I'm asked the importance of science, I can easily wax lyrical about we tried to find black holes, we didn't get there, but we invented Wi-Fi, and or how GPSs require understanding of general relativity, which you might have thought was rather esoteric. But really, when it comes down to it, the reason that we do science is in many ways because it enhances the human experience in the same way that music and theatre and art does. That's in these kinds of conversations, I'll risk quoting Richard Feynman, who said something along the lines of, science is a bit like sex. It might have some practical consequences, but that's not why we do it.
Alan,
yeah, look, I think it's important not to be polarised about these things.
Keep your mind on the job, sir.
It's important not to be polarised and sort of see that things have swung too far. I mean, we've spent billions on the Large Hadron Collider, and the SKA, the Australian government's just investing more money in. We've got the Hubble Space Telescope. We've got wonderful investments, huge investments in pure science, and I think it's fantastic. More of it. We've got to do it. But we also need to have a balance with translation of science for economic and societal benefit. So I don't
Is that Wi-Fi thing a classic example of where we could have done a hell of a lot better?
It's not as simple as all that. Wi-Fi was, the contribution to Wi-Fi is across the planet. Hundreds of people, hundreds of companies have contributed to Wi-Fi. The CSIRO invented a significant thing that improved an aspect of Wi-Fi and has earned hundreds of millions of dollars for that. So I think it's a good thing. I wouldn't be doing the woe is me. What we need is a balance between pure science, applied science, the translation wherever we can for benefit of society.
Okay, Emma, I'll give you the last word. We're running out of time.
I love the last word. But Alan has really summed it up very well. It's all about balance. And I started at the beginning saying clever governments fund research that takes a lot of different approaches, and clever governments do basic research and applied research. You never know when the laws of physics are going to come in handy. And you look at the climate models, they're all about the laws of physics. And they're the things that are going to mean that nobody has to cry when their crops are lost or their house is flooded or, the bushfire rages. We use science to help understand our world. Often it might be made into a gadget that we can sell. Sometimes it's made into a way of preventing disasters. It's always useful, and you just never know when.
Okay, that's all we have time for tonight. Please thank our panel, Brian Green, Upali Devasakera, Tamara Davis, Alan Finkel and Emma Johnson, and also Jacinta down the front there. If you don't mind, I'll thank you as well. Thanks to all of you, and thanks for your great questions. Now, next Monday, Q&A will be live from Melbourne with Victorian Premier Daniel Andrews, the Minister for Resources and Energy, Josh Frydenberg, Independent Tasmanian Senator Jackie Lambie, Bank of Melbourne Chair Elizabeth Proust, plus columnist and social media force Clementine Ford. Until next week's Q&A, good night. you.